Thank you. I suppose that you can hear me in the back. So thank you for the introduction, and thank you for the invitation to give a presentation at this symposium. So I will talk about an important problem, which is the use of large language model or large reasoning model or foundation model as a research assistant in the research that we develop, and the need to establish a methodology in order to trust these models to help them do our research. So I lead the team at Argonne, and I'm also the lead for the evaluation of the AuroraGPT project. And what I will show you today is the result of the work of many, many people, including the team of the evaluation for AuroraGPT, but also other people who contributed to, for example, the generation of benchmarks. So I will start by giving you a little picture of what is the current situation of these models. So we are talking about large language models. They have improved drastically in the past 4 or 5 years. If we look back at GPT-3, for example, 2020, and what we are seeing now in terms of performance for mathematics or for science benchmarks, we can see that these the model have improved drastically, and it kind of changed our perception of what could be done with them in the future, and open the possibility to think about using them as research assistants. So they are good for text processing, of course, summarization, extraction, translation, classification of data. But what is really important to us is also being able to process mathematics and to respond correctly to scientific questions. So you see here some benchmarks that are interesting, just to show the progress between ChatGPT 4.0 and 0.1, just in the past year. But things seemed at some point to plateau. This was before 0.1 happened, and essentially because the progress of this model were coming from the increase of their number of parameters and so the size of the data that was used for their training. So we were kind of stuck with that situation. Then 0.1, OpenAI proposed 0.1 in September. And what changed here is that this model has been trained for 2 reasons. And it used different techniques like chain of thought and reinforcement learning during the training in order to do this reasoning. And during the inference, it used chain of thoughts in order to explore different solutions and then take the solution which is the most likely to be good. So that's what happened in September. And then we heard like 3 days ago that another model, which is called DeepSeek from China, it's an open source model, in fact, succeed to reach almost the same performance as 0.1 on important benchmark for us, like for example GPQA, which is a scientific benchmark. And just 1 day after that, there was another announcement from another Chinese model, which is Kimi 1.5, and same thing, trained with reinforcement learning in order to learn to reason. So these models are push the large language model into these large reasoning models, and this is the new axis of improvement for these models. And so this is good to be able to respond to MCQs or multi-choice questions or to questions in physics or mathematics. This is also good to try to understand if they can do more symbolic reasonings, for example. And that's what is tested with this RKGI test, which is super easy to solve for human, and what's extremely difficult to solve for the previous models. What you see here is the performance of O3, which is the new model from OpenAI. And so this model succeeds at 85% in its largest configuration, most expensive configuration, to solve this model that probably a kid in the 6th grade can solve all of them easily, right? But so this model solved this problem, which was not solved before. It requires a lot of skills to do that, which are reasoning skills. So I will not list them. You can see them on the screen, What's important to understand here is that for every task to solve, so what you see at the screen is just one task. The model is just asked to find a configuration where you have this little guy in yellow, so looking at these examples. And to solve just one task, it was taking 13 minutes. And one task like that required the use of resources that costed several thousands of dollars, just for one task. 13 minutes, several thousands of dollars. And to solve this benchmark, or to test this benchmark, you need to solve hundreds of these tasks, right? So this gives you the notion that these models are very powerful. Yes, they are very, very powerful, but it's also very expensive. What is also very important to us is their capability in mathematics, and there was this frontier math benchmark that has been produced, and which is an extraordinary benchmark that was built with people, field medal winners and other top mathematicians, and with the notion of generating problems in maths that are exceptionally hard. So I cannot solve even one of them, right? It's very, very, very hard, and it's in very different disciplines. And the idea here is that if a model succeeds to solve these problems, it will be even better than a human because it will be able to solve problems in very different variety of mathematics. And so that's a very impressive result that O3 just did, which is to succeed at 25 of these different problems. 25% of these different problems. This is an important result, and this suggests that if the trend continues like that, there is a possibility that improvement will accelerate again. So I think it's important to realize that these models are increasing in their capability very quickly, very, very quickly. And it's hard for us to keep up and try to understand how we can use this model, we can trust this model or not for science, right? So we need to understand that. So these LLMs or foundation model have been used by scientists in different approaches. You see here for essentially specific tasks, predicting molecular properties, uncovering genomic patterns, or solving mathematical problems. But what this situation suggests is that, in fact, we could imagine using them at every step of the research process. So what you see here is the diagram that was published in Nature with this notion that, in fact, this is the scientific process. If we can use AI in these different steps, from generating the problems to generating hypotheses, looking at literature, generating tests, and assessing the result of these tests. If AI can help in all of this, this will accelerate drastically the science. And that's what is important here. So what do we mean by a research assistant? Well, that's this thing where you start with a research question. And for all the steps, you will use AI as an assistant to find solutions to the problem, the task that you are doing during this cycle of research. But I should say that this is a very ideal representation of research. In general, it's much more complicated than that. You jump between these different steps because you get stuck, and you need to imagine new solutions, and you restart the cycle. So you start with your problem, you do a study is literature search, essentially. You're generating some initial data in order to be able to generate hypotheses, to try to find some solutions to your problem. And once you have generated this hypothesis, you go to the test stage, which is to do simulation, experiment, or observation in order to collect data. And you analyze this data, you assess this data, and this gives you the notion whether or not your hypothesis is verified. If it's not verified, then you have to redo the cycle. If it's verified, you write a report. So if we look at the current situation, you can already use these models to help you in these different tasks. We do that, and maybe you do that in your labs already, using these models to help this scientific cycle. So I will give you an example. This is an image of the best paper from HPDC 24. So we were lucky to get this best paper award. And what we wanted to do is to use this diagram in order to see if the model could, in fact, help us to reproduce this result, right? So let's imagine the model doesn't know about the paper. Can we ask the model to help us solve this problem? So what we did is that we formulated the problem, simulated the problem to the models. We tested several models, and we did the literature search, solution extraction, solution identification, code generation, or principle generation and system design in order to solve these problems. So that's the type of thing that we wanted to do to check if, in fact, this model could really help us. So you will see later in the presentation what is the result of this experiment, but that shows you how we could use these models. So what do we want for an AI scientific assistant? Of course, we want it to have scientific skills, so we should be able to reason, to do math, to understand literature. It needs to have integrity, but it also needs to be trustworthy. And that's really the thing here. We need to trust the result that we get from these models. In particular, if it takes 13 minutes to get a result that will help us, this result, we don't want to spend 2 days to evaluate if it's correct or not, right? So we need to make sure that when we get a result, we can trust the result, and we don't need to spend a lot of time verifying what the model is saying. So that's a very important aspect. And then, optimally, what we would like is that these models are capable of producing hypotheses, and that's probably where they currently fail. Even the best model today have some hard time to generate hypotheses, and we hope that at some point this is where the progress will happen. A very important aspect, these models should be safe. So that's also critical here. They should be safe for the user. So this means they should not be toxic, right? But they also should be safe for the community. So the idea is that you cannot use them to generate or to design harmful substances. So it's really, really critical to have that, and that's why you need to include that in any methodology that will evaluate this model for science. So if we look at the current situation, if we really want to have a broad adoption, or broader adoption of these models, we need to solve 2 problems. First, we need to develop methods to analyze their performance deeper than what we have today. I will show that. And the second thing is that we need to make sure that we develop also the trust the trust that we have in these tools. And for that, too, we need to develop a new methodology. So it needs to be a comprehensive, rigorous, accurate, transparent, and community-approved evaluation methodology. So if we look at the state of the art, what do we have? So essentially, when you want to evaluate these models, you need to look at the black box, right? We don't know what's inside, or we know what's inside, but it's very hard to understand what's going on inside, in particular with the size of these models. And so the only thing that we can do is to inject inputs and check the outputs and see if the output corresponds to what we thought should have been done with this input, right? So that's the way we do the evaluation of this model. So black box, and we use the dialogic interface or the multimodal interface to be able to assess their characteristic. And currently, what we have for that are 2 types of benchmarks, or which are made of multi-choice questions. So I will use the term MCQ, and benchmarks that are made with open responses, so a question and a response which is free-form that we need to evaluate. So MCQs are easy to evaluate. The response of the model is trivial to evaluate, but it's very, very difficult, in fact, to generate MCQs. It doesn't seem difficult, but if you ask researchers to generate MCQs, it's not that easy. You need to find interesting questions. You need to have distractors that are not trivial to discard and distractors that are not too close to the solution. Otherwise, this will be confusing even for a human, right? So it's hard. It's not easy. So when I will mention that some of these benchmarks have 400 MCQs, don't think that, well, this is a very, very small number. It's not a small number. It has been extremely difficult to do that, right? So that's an important aspect. Open response. So it's much more difficult to evaluate. It's open to interpretation. Even two humans or 3 humans will not agree on the quality of the response, for example, but it's more easy to generate. So you have to deal with these two things. There are in the literature a lot of benchmarks that have been proposed, MCQs or open in different domains like material science, chemistry, biology, climate. You have a lot of benchmarks that are available that use this type of techniques. But in fact, what they test is not necessarily interesting for everyone. It's not helping us to trust these models, for example, for in general for the tasks that I have described. So because they do some very specific tasks, or they test some very specific tasks that are classification, clustering, or summarization. So this is not exactly what we need. So we cannot only rely on this benchmark. The other thing is that most of them are open. They are publicly available, and there is a risk of contamination. So this means that there is a big risk, and in fact, it's not a risk. It happens that these benchmarks are in fact used for training the models. So then it's not surprising that the model is good on this benchmark because they've been trained on them. The best that we have today is called GPQA. So that's a benchmark that has been developed to be at the level of PhD and beyond. And so there is 480 questions in this benchmark. But again, it's very hard to get to that number and discover different domains. It's a significantly difficult benchmark. So experts reach only 65%. So if you are an expert on a particular domain here, you can succeed at 65%. You will not get 100% in general. Okay, the problem here is that OpenAI with O1 obtained 78%. So which means that this benchmark is what we call almost saturated. So that means that it's informative, but it doesn't allow to test the capability of the model beyond that point, right? And that's what we would like to do. So that raises the problem of how do we generate benchmarks that are increasingly difficult, right? And that's an open problem, which is also very hard. And so what is important here is that it's also missing domains that are important for us, like climate, computational science, and biology, but it's normal because there are not that many questions. By the way, O3 reached 87% now on this benchmark, right? So this is even better. So which means that we are really close to the saturation of this benchmark within other benchmarks. So gap analysis, MCQ benchmark, we need to think about a benchmark that we can generate with many questions, probably more questions, but that could scale, but also that increase in difficulty. So that's one thing that we should think about. Open response, we need to figure out a way to do an automatic verification of the questions, but also validation of the response. But one thing critical is missing here. I mean, we talk about benchmark, we don't talk about the reality of the research, right? When I'm developing a research problem, I'm not responding to some questions that are static. I'm really developing my research, right? So that's the reality that needs to be captured, right? And that's how we should focus, in fact, that's what we should focus on when we develop this method of evaluation, and I think this requires new techniques. So that's what we did in this work, which is establishing a method. So this is part of AuroraGPT, and we have a team working on that. And really the goal is to see how we can develop methods and tests to evaluate the capabilities of LLMs and large reasoning models as research assistants. So the methodology is in progress. It's a work in progress, but I should argue that it will always be a work in progress because these models are progressing, and so the methods to evaluate them needs to progress as well. So, and we will probably need to add more and more methods as the capabilities increased. So what you will see here is a snapshot of the methodology as of the end of December 2024, and I will mention the lessons learned so far. We are writing a paper on what we have learned. And so this thing will be available on archive soon. So just one thing, we started just 12 months ago, so you will see that there is still some holes, and it's a work in progress. So what do we want to do? We want to assess scientific knowledge, analyze scientific reasoning capabilities, appraise effectiveness in research tasks, diagnose source of weakness. That's a very important aspect, because if we want to improve these models, at some point we need to communicate the weakness that we have discovered. We need to communicate that to the public so that the people who are developing these models can improve the model that at the end we will use, right? So this is to our benefit to communicate the weakness that we will see in this model. So diagnosis is a very important aspect. And this is a very challenging problem because these models are evolving, as I mentioned, at a pace which is extreme, so we need to adapt quickly. And we need to work in an enclave, because if we start communicating our evaluation, for example, the question in the benchmark, then this will be used for training, and that will completely bias the results. So we need to evaluate different skills. I already mentioned that. I will not go into the detail here, but a lot of skills needs to be evaluated. We have criteria to evaluate all these skills in order to assess the performance of these models. And of course, we need to add safety here. So that's the methodology. You see MCQs. They should be part, because MCQs, if at large scale, in fact, can test the breadth of knowledge of a model. And that's something we need to capture, to understand. The open response benchmark are also part of this methodology, because we need to understand in depth, in fact, the knowledge of a model, but also its planning and reasoning capability. But where the reality happens is on this end-to-end new evaluation methods that we propose. So it's called lab style experiment and field style experiment, where in fact we test ourselves this model, we use them as a scientific assistant, we score them, we analyze them really as if they were our assistant, and try to understand their weakness. You see that we have some cross-cutting aspect here, so trust and safety, but also uncertainty quantification and the development of a platform to be able to run all these tests. So this is the coverage of the different methods based on the different steps of the research that I have mentioned in this cycle of research. So this is the vertical aspect, and you see what these different techniques cover. There is some overlap, and that's normal, because some of these techniques are really focusing on precision, and some other techniques are at scale, and so that's why we have this overlap. So I will show quickly a few of these results that we have, what we have learned. First thing is the astro benchmark. So the idea here was to develop a benchmark on astrophysics just with automatic MCQ generation. So for that, the team used about 1,000 articles from the annual review of astronomy and astrophysics. And we used a model to generate MCQs with 5 questions per paper and 4 distractors. And 200 of these MCQs have been manually validated. So automatically generated, manually validated. And if you look at the result, you can see that Claude 3 Sonnet, for example, is very close to saturating this benchmark. It's not because the questions are not too difficult, it's because, in fact, all the papers are in the public domains, and so the models have learned this aspect. But what we have seen here very quickly is that manual validation is the bottleneck. So when you want to develop a benchmark like that, what really is difficult is the validation, because you need the people to validate, and for now, and that's the limit of this. And it's important to consider that the scalability limit of this is the people who will validate the model. So in order to see if we could develop a benchmark that will adapt, and we have developed this AI for Science MCQ benchmark. This is a platform, an exploration platform to design benchmarks, right? To try to find ways to make benchmarks scalable, and to find ways to automatically verify the quality of the questions, but also the generation of the question, and also the validation afterwards of the response of the model. So that's a research platform. So we have generated about 1,000 questions, 720 manually, 260 automatically with the GPT-4. And so what we did is generated MCQ from papers, and there have been about 600 manual review of these MCQs, and 317 have been validated. So this means that we consider them as relevant. I mean, 254, sorry, have been accepted, so which means that they are relevant. So we start with 1,000, we end with 254 accepted, considered as good enough to be part of this benchmark. So the first question is, how does it compare to GPQA? Because we said that GPQA is the standard, so the idea is to look at how well we do. And so if you look at the situation, we tested with 5 shots, 5 examples before the actual questions. GPQA has 4 distractors, which means, has 3 distractors, which means that the random choice is 25%. AI for Science has 5 distractors, which means the random choice is 20%. And so if you look at the results, it's not easy to see, but the first cycle on the right is GPQA for Llama 3, 7B Instruct from Science Leaderboard, and this is GPQA, so that's about 50% of accuracy. And if I look to AI for Science, it's 37%. So that plus the difference in the number of distractors makes this benchmark more difficult, in fact, than GPQA. So this benchmark is more difficult than GPQA, right? So that's an important result. The other important result is that inside these 254 MCQs, there are 71 that have been generated with AI, that have been automatically generated. So which means that the quality of the question that we have automatically generated match the quality of the question that have been generated manually, right? That's very important for the scalability of the benchmark. This means that we have a way to scale and generate more questions and keep this quality. Then we have also looked at how we judge the quality of, in fact, these generated questions automatically, so not manually, but automatically. I will not explain that. We use LLM as a judge for that, and for now it's improving, but it's not yet there, but we are working on this. Okay, so the conclusion or the lessons learned here is that manual generation of MCQ is difficult to scale, and we really need to work on automatic generation, automatic validation, automatic verification of these MCQs. And what's important is that when we generate these questions, they need to be at a level which is good enough or hard enough, and that's what we did so far. So there is another benchmark that we have developed. It's called SciCode. I think it's a very important one. So it's a benchmark that focuses on coding. It uses mathematics in domain of mathematics, physics, chemistry, biology, and material science. So there are 80 problems that are numerical methods or simulation of systems. They compose into 328 sub-problems. And what we ask the model to do, in fact, is to solve the problem, generating a Python code. Then we execute the Python code, and we compare the result with a gold standard, right? And if the results are approximately the same, then we consider that the result is correct, right? So that's the way this benchmark is working. Of course, I'm missing a lot of detail there, and you should look at the paper. What's important is that O1 succeeds only at 7%. 7.7% on this benchmark, which is, for now, the most difficult benchmark available to do this type of test, right? So it's a very important benchmark because it's extremely hard even for O1. O1 succeeds at 28% if you decompose the problem in sub-problems, right? Okay. What about the reality? I have only 30 seconds to finish that, or maybe 5 minutes. So, as I said at the beginning, in fact, benchmarks are interesting, but what we really need to do is to develop methods to do the end-to-end evaluation, the full cycle of the evaluation, and that's what you see here. So that's something that I did so exploring a quantum entanglement problem with Argo, which is a version of OpenR1 preview that run at Argonne. And you see the cycle of research there, but you see at some point that we got stuck with the colleague. We could not progress anymore in solving this problem, and we had to redefine or deviate a little bit the problem to restart, in fact, the cycle. So that's the reality of research. So I did experiment like that in 4 different domains, so DAG scheduling, PDE solving, and the best paper of HPDC, reproducibility of that, quantum entanglement. And when you do this type of experiment, you try to solve the problem. It takes time, about 6 hours per experiment, and you collect all the information that you need in order to do an assessment. It takes 25 hours in total, more than 100 prompts. And you test many different models at the same time to be able to compare them. So as I said, we did that on this HPDC base paper that we tried to reproduce. And we got something like that, which is you look at the different steps, or literature search, solution extraction, solution identification, different aspects of the research problem, and then you score the models according to their performance. Here, it's unfair because Perplexity Pro is a RAG, and it has the paper in his vector database. So he can answer very quickly the problem, and he can find the right solution because it has access to the paper. The other models don't have access to the paper, and so they fail miserably, essentially. Except O1. When O1 appeared, we retried this problem, and O1 training ended before the publication of the paper. So one doesn't know about the paper. And you see that he has a lot of correct. So this means that these models are improving in their capabilities. And this method also is able to track, in fact, the progress of these models. Another thing that we done recently, and this was a training that we did at Argonne. So the goal was to introduce the large reasoning model to researchers, and it was a training session using Argo, which is, again, a version of O1 that we use at Argonne. So there were 200 researchers, and you see the picture of that worked together at the same time for 2 hours to solve the problem that they were interested in. And in total, they tested 134 scientific problems. And so then, the feedback that we got from them about this experience, this training is the following. They really consider that this model would be more useful if we could interact with HPC experimental code or simulation, if they could understand and analyze multimodal data, which was not the case at that time for Argo, if they could integrate better context from scientific experiments, or longer context, essentially longer data, generate correct references. So that's also something that people really want, is that when you ask a response, you want to have references and correct one. Provide uncertainty also in the result. Does the model is firm on his answer, or does the model hesitate? So that's something that would be interesting to have. Produce more detail in the response, and improve the knowledge of scientific topics. So it seems that some of these models were not on par on some scientific topics. But the most important aspect that people have understood is that, in fact, there is a lack or weakness, strong weakness in originality and generating new ideas. So that's where these models fail so far. Okay, so that's where we are, hypothesis generation. So now, if we really want to turn that into a scientific method, we will need to develop ways to capture the interaction, to score this interaction, to comment. So the user will need to assess, in fact, the nature of the interaction, the quality of the interaction, and from there we could do some large-scale analysis of all this interaction between the researchers and the model to try to understand where is the weakness and diagnose. And this diagnostic will certainly be very helpful to improve these models and at the end help us in our research. I will not talk about the safety. This is a very important concern. We have integrated into the methodology decoding trust, which is a benchmark to test toxicity, bias, stereotypes, and the harm to the user. And we also integrate WMDP, which is a test to detect possibility of a model to be harmful to the community by developing a weapon of mass destruction or helping you to develop weapon of mass destruction. So the idea here is to make sure that the model cannot do that. What's next? So we will continue the benchmark development. We will do more lifestyle experiment to improve the method. We'll do more field style experiment to improve the method. And something that I didn't discuss is that we need to develop a frontier science benchmark, which is the equivalent of the frontier math benchmark. Very, very difficult problem, extremely difficult problem, but the top experts to test these models as much as we can. I should say that at some point, you could imagine that these models will solve these problems, and then we will have to find even more difficult problems. So if you're interested by all these questions, please come to the hackathon at Kobe in March. We will discuss about this problem of evaluating these LLMs for science applications. Thank you.